In this lecture, I'm going to talk a bit about the wave-particle duality, and particularly what it means in terms of light. First, let's figure out what's different between a wave and a particle. In the last few lectures, we discussed what exactly a wave is, so let's go over that. First of all, a wave transports energy. This also means that the wave is constantly in motion because it's transporting this energy. Another key feature of waves is that they're periodic in nature, which means that there's some sort of oscillation going on. For example, in a sound wave, pressure oscillates, meaning that it changes between one value and another. The same goes for a light wave, which is an oscillation in magnetic and electric fields. A particle, on the other hand, is made up of matter instead of energy. This means that a particle takes up space, whereas a wave does not. A particle may also be stationary. Just like a desk can sit in one spot, a particle can always stay in one spot. This is different from a wave, which is always in motion. However, a particle can also be set into motion, such as a baseball that's being thrown. If I were to draw out a wave, I would make it look something like this to represent the oscillations, whereas a particle would just look like a point. So it sounds like waves and particles are pretty different, but according to the wave-particle duality, light is both a wave and a particle at the same time. When we're talking about light waves, we often refer to EMR, or electromagnetic radiation. When we're talking about a light particle, we often say a photon of light. This seems pretty strange. How do we know this is true? This has been tested experimentally by looking at how atoms react to light. So let's say we have a positively charged nucleus of an atom with a couple negatively charged electrons orbiting around it. So we'll put some electromagnetic radiation in the mix here, some light waves hitting these electrons. What you might expect if we drew a graph is that the more energy you had in the light, the more electrons you would see being ejected. This electron ejection is what happens when energetic radiation hits atoms. So using this wave model, if we drew a graph with frequency of the light on the x-axis, frequency is proportional to the energy of the light. And if we put the number of ejections of electrons on the y-axis, we would expect to see a nice linear curve like this, because the amount of energy that's being applied to this atom would be proportional to the number of electrons that get ejected from it. But when experiments were done, this isn't what scientists observed. Instead, they saw something that looked much more like this. There's no electrons ejected until we reach some special frequency at which a certain number of electrons are ejected. It's important to note that this is for a particular intensity of light, so the total energy of the light is the same no matter what frequency we use. This is much easier to explain if we think about light instead as a stream of photons, of individual particles. If we have a photon of light traveling toward this electron and it strikes it, the electron will be ejected only if the energy is greater than some threshold energy. This would be the same for a wave, but in the case of a photon, it makes sense that this is dependent on frequency, not total energy. In this case, we have a binary choice because it's only dependent on this particular photon and this particular electron. If we draw a graph, we would expect that if the frequency of that photon is below the threshold frequency, F naught, then the ejection will not occur. But if it is above that threshold frequency, the ejection will occur. If the frequency is higher, it only means that the electron will have more energy when it leaves the atom. We can't possibly have more electrons ejected than this one because we're concerned only with the interaction between this particular photon and this particular electron. We can have more electrons ejected per second if we increase the intensity of the light, which means we increase the number of photons per second. This wave-particle duality also holds for other things, such as electrons and even larger particles.